Hello, my name is Andrew Salutis. For my final project, my goal was to implement the complete manipulation pipeline from seeing a hammer to swinging it into a target. As part of my research, I've designed a quasi-direct-drive manipulator arm which I wanted to model and use for this project. Typically, an old-school position-controlled robot arm would struggle with a task like controlling the impact of a hammer, which is why I wanted to attempt that task for this project. To employ more tools from the class, I also wanted to be able to use a vision system to locate the hammer and then plan a trajectory to grasp the hammer and wield it. This is a quick overview of the system that I ended up implementing. I didn't completely reach my goal of controlling the hammer impact, but I was able to establish the overall system architecture and test the two subsystems shown here independently, in blue and yellow respectively. The pick-and-place system consists of perceiving the hammer, the environment, planning the grasp for the hammer, and then generating and executing a pick-and-place trajectory to bring the hammer to a known goal location. First, the hammer is placed randomly in the environment. Then, point clouds from 3 separate cameras are each segmented and merged to get a global estimate of the point cloud of the camera. The grasp is planned directly on this point cloud, with a cost based on antipodal points, the geometric center of the point cloud, the maximum distance between points that are within the gripper fingers, and the color of the points, which is an attempt to orient the hammer correctly within the gripper fingers. Finally, the pick-and-place trajectory is generated using keyframes, which move the hammer from the initial pose to a goal configuration. The swing trajectory system uses a series of inverse kinematics problems to create an initial joint trajectory that will bring the hammer face to the desired impact location. Then, the trajectory optimization is performed to try to achieve a desired impact velocity. This optimization is formulated as a direct transcription problem, and I've constrained the initial and final states to be the same as those of the inverse kinematic trajectory. There's a running cost on the sum of the inputs to minimize the energy used during the trajectory, and also a terminal cost on the impact velocity to try to achieve the desired impact velocity. Here are some results from the pick-and-place subsystem. The leftmost image shows the top 5 grasps on the hammer out of 500 that were generated. The middle video here shows an example pick-and-place trial at double speed. And finally, the rightmost plot shows the initial and final hammer poses for 18 trials. Of the 18 trials, 15 were successful in that the hammer was close to the goal location and the orientation was accurate. This is good for an 83% success rate. Here is one example trial from the swing trajectory system. The keyframes from the inverse kinematic C trajectory are shown, as well as the initial and goal frames for the hammer face. On the left, 4 key screenshots of this trajectory are shown along with their timestamps, as the hammer flips over and impacts the face of the cylinder. The video on the right shows the optimized trajectory at real speed. In conclusion, I created a pick-and-place system that can locate the hammer in the workspace and return it reliably to a goal configuration. I also created a swing optimization system that attempts to hit the target cylinder at a specified impact velocity. Together, these are 2 good building blocks for the overall system that I wanted to create. If I were to keep working on this project, some of the next things that I would address are making the simulation more realistic by improving the modeling of the arm and the hammer, and adding more realistic noise to the perception system, as well as improving the formulation of the trajectory optimization problem to get better swing results. Thanks.